I wonder if I screwed up the DRAM part of the schematic. Oh, wouldn't that suck? Let's just cross our fingers and hope the cable wasn't in right. No, it doesn't work. All right. These chips are probably destroyed, although they're not hot. Don't know what's up with this. Okay, DRAM's out. Store them on some anti-stat here. Off to the side. Plug it back in now. Yeah, that's not good. That's not a good sign there. That's a bad sign. That's what that is. Well, I suppose it's possible that we could have bad chips. It's time to look closely at the schematic at this point. All right, so here is the dynamic RAM chip, and this is actually the TMS chip here from Texas Instruments, all right, earlier. Part number, but it's the same part. What do we got here? We have one is G bar, okay. And 2 is RD, DQ1, DQ2, 3, 4. So we got 2, 3, 15, and 17. So that's 2, 3, 15, and 17 are the data lines, okay. 4 is write bar, 5 is ras bar, 4 is write bar, 5 is ras bar. What do we got? So A0 is 14, 13, 12, 11, 10. So 0, 1, 2, 3, 14, 13, 12, 11. So we got 14, 13, 12, 11. Well, these are not likely to be a problem since we got a power problem. It's probably the power pins. Or I soldered the thing in wrong or something like that. So A4 is on pin 8. Yes. A5 is on pin 7. A6 is on pin 6. A7 is on pin 10. Okay, so there's the data and the other ones. What do we got? The CAS is on 16. All right, so we got 18 and 9. You know, it wouldn't be the first time. This is always 5 in ground, but the ground is the what the son of a these idiots. So nice. So this is not 5 in ground like every other chip of the era. It's the other way around. 5 is down here and ground is up. This is stupid. So I may have fried those chips. Fortunately, I got spares. This is so stupid. God. Why did I? Yeah, okay. Dumbass. So the situation is that VDD is 5 volts, obviously. It says right over here. And this is supposed to be ground. So I probably wrecked the chips, but you never know. I mean, they quite often have like protection diodes and things like that in there. And this may have just shunted the power through. Didn't leave the power on long. If I left it on a long time, it'd heat it up, burn it up, and all that other fun stuff. So what I could probably do, just for fun, since this is obviously shot now. Anyway, I knew there would be a problem, but I didn't think it would be this stupid. No, I have these stress chips. So what I'm going to do is bend this pin out, bend that pin out, shove it back in the socket, and then hack some wires from here to where it belongs, and from there to where it belongs, and power it back up. Oh, this is dumb. So meanwhile, I will also fix this so that at least this isn't moronic and incorrect. We'll just put... I'm going to go edit this footprint. And I'm going to rearrange, I'm going to also rename this idiotic thing so that it matches the sheet. You know what, I almost always do these backwards. So what I'm going to do is I'm going to just call the damn thing ground in 5 volts. So I don't screw it up again. Idiot. 5 volts is on pin 9, right? So here's the thing. VDD is the drain, and that's my 5 volt power supply. Stupid. Pin 9, 5 volt power supply. 18 is up here, is VSS, and VSS is ground. Now, because I edited this from the schematic, all right, if all I need to do is save it and close it, and it should annotate this schematic that I had open, right? And the way I did that is I selected it and I hit Control E for edit. Now, this is KiCad 5, and KiCad 6, this may be a little bit different. Now, because I like to have the grounds going down and the 5 volts is going up, and the way these are arranged is upside down for that, and I'm editing this thing anyway, I can just move these pins around. Come on. And make it so that I can do that more easily. Control S and Control Q. And you can see that these have now been reversed around. And actually, I can put it back the way it used to be since it's now correct. And we can double check over here and we can see that this is correct as well. All right. Save all this. Bring this back once again. And see that VDD is 5, and that's on pin 9 right there. The other one's ground. So 5 is on 9, and pin 18 is ground. Completely backwards of every other thing. This is the kind of crap mistakes I make, you know. You watch out for everything else, and then some dingus puts the power and ground pins backwards. Why should not have I thought that, right? TI does all the address pins backwards. Why doesn't it do the power backwards, too? Oh, all right. There's a waste of $20. Now, at this point in time, if we bring in the, the new design updates, you can see in here, oh, I'm changing ground to 5 and 5 to ground. I can update the power thingy. They're actually connected to the wrong thing. Okay. And if we turn on the power planes, you can see that this pin that is now ground is connected. You can see the thermals to the pink layer, which is one of the inside copper layers, which is going to be the 5 volt layer, right? So this is all wrong. If I hit Control B, it will redo the copper pores. Capital B, I meant, not Control B. And it will redo the power planes and connect it to the correct thing. So you can now see that this pin is connected to the ground plane on the front, and most likely the back should also be connected, right? But no longer on the pink one, which is the inside power plane right here, right? And the 5 volts down here, which is totally weird on the wrong. I wonder how many people have tried these DRAMs in a breadboard. Let me know in the comments below. This is just insane to me that anybody would reverse these pins in this exact way during that era with parts in an 18-pin dip like this, I'm just shocked. It's just terrible. Oh man, who thought this was a good idea? Ouch. Well, it's my first DRAM experience. What was yours like? How many of you have fried one of these things? I'm guessing more than zero. Okay, so to sort of hack this, what I'm going to do, since we know we have to have ground here, but I have my board as power here, and vice versa down in this lower left corner here, what I'm going to do is I'm going to take this pin and I'm going to bend it out. Now, these chips are really close together, so if I bend it out straight, it's going to reach over and hit the other chip. That's one of the problems with having it this dense. But if I bend it out, the pin can go down between the sockets like over here, okay? And the same thing can happen with this one down here, and this one can stick out as well to the left. So if I bend them out, or I can just bend them all the way around so they stick up in the air, and I can do that too if I have a worst case scenario. Now I stress these two chips, they may be broken, I don't know. When the power comes on, they probably get filled with it probably has some sort of patterned garbage in them, but they'll have something in there. And maybe what I'll do is I will just do one of these two chips so that there's garbage in there. And if I can bring on the VDP just enough to start reading data out of here and trying to draw a screen, maybe there'll be random stuff on the screen, that would be great. And if there is random and nothing is heating up to 1,000 degrees, maybe the DRAM's okay. And then I'll put the second one in there and we could try figuring out some test code or something like that. But at least we could get the thing powered up, maybe. And we got nothing to lose with those potentially wrecked chips anyway. So that's what I'm going to do. I'll just put a little wire wrap on the pin with it hanging off to the side. Now I'm going to have to get these things connected up to power somehow. I could come up and connect it here, but the little surface mount capacitor on there will unsolder itself very easily if I start trying to put wires on here as well. So I happen to know we've got a handy power and ground right over here. We've got a couple of grounds and a couple of power pins right there. It's not optimal at all, and there are no bypasses that are nearby, and DRAM's got a lot of power draw. We'll try it. I'm going to try and run the ground, which is over here. I'm going to run that over to here, and I'm going to run the power over to the power, okay? And then we'll just boot it up and see if we get random garbage. All right, so here's the chip, and you can see I kind of bend that pin out a little bit there, right? I'm going to do the same thing in the opposite corner here. Again, we probably got nothing to lose because these chips could easily be shot anyway, all right? Now, when I plug it back in the board, I got to be very careful and make sure that these pins, you know, do the right thing. That one's out over there. This one's going to be out up there, all right? But before I put it on there, I'm going to grab my twisty wire wrap tool, and I'm going to put some wires on this thing. And after all this, I'll probably hook it up backwards again. So we got to be careful, all right? I'm going to do about a 1/2 inch. We don't need a lot of wire wrapping. Just enough to hold it on. Just to test my ineptitude of this situation here. All right, I'm going to wrap it around a couple of times. Should be more than enough to do the job. All right, so it's like a spring wrapped around that lead, okay? Well, it doesn't need to be very long, right? So only just a couple inches here. All right, so it's going to go like that, and then I'm going to hook it up. This is the backwards ground pin, okay? Now I'm going to do the other one down here. Again, we'll strip off an inch or so. Normally when you do a wire wrap job, you want way more wraps than this. This looks like it's only going around 3 or 4 times on there. Usually you want it many. This is enough for this situation here. Done this before for different reasons than having the power backwards. This is just unacceptable. All right, so there's the other one. And again, for now, we're just going to do the one chip. If we get this all to go and it isn't fried or anything, then this will be nice. You can do them both. Well, I mean, we'll make this board go. This is a minor setback, a minor blemish of the situation here. How much do I need on there? Yeah, that's funny. Get this spool out of the way. Okay, see if we can get all these pins in there. One out. Okay. Okay. See how that's out of there. All right, the same sort of thing on this top one up there. Come on. Get in there. I think this one's not bent out enough. Again, you can bend them all the way to the point where they're sticking up in the air if you have to. In a situation like this. Come on, get in there. What's it hung up on over here? There we go. Just give it, you know, an extra 20 pounds of force. That'll do. I think the answer is, given how much more of those stick out the sides, all of a sudden, they needed to be bent out a lot more than I had them in there, all right? So the thing is, we got to be careful that the ones that are between the sockets here don't short the chips together. That could be a bit of a problem. It's all right if this thing sticks out a little bit. Now, backwards. Normally, this would be ground and power. We know it's backwards. This is power. This is ground. We know power is in this upper hole here. Ground is down there. So let's go ahead and strip these off. All we need now is just a little teeny little bit of wire exposed. This is awful. All right, so ground. Well, we can go ahead and use the nearby holes. That's the ground one. Now, if you have different color wire, it's handy to use, you know, like this red for power and black for ground or something. So, ground is in the upper right-hand corner. I didn't do something dumb like get the pin 1 orientation backwards as well. This is so embarrassing. Okay, so this one up here is goofy ground, backwards ground, right? If this was a snowboarder, this would be goofy foot, right? And this one down here is the power, where no one on earth would ever put it. And that is the upper pin there. Now, I should be able to turn it on, and the power LED should go back on. Don't know if I need the scope ground connected anymore, but I do need this little here to make sure the video goes out of the board, along with this little pressure with this guy. Well, here goes. We can see the LEDs come on again, and normally they flash. What's this one going to do? There it goes. It flashed. Okay, let's boot her up and see if this is heating up. This is the time where you got to be careful when you touch it. A fried DRAM can get real hot. Well, I consider this a bout of great luck. The fact that this is actually booting right now is amazing. Of course, that DRAM may be dead. I don't know. So here's the video display. It's not doing anything interesting. So let's move off to the side here and run our DDT, set up our program, and initialize the chip again, right? A100. You know what? I should have saved this program. I'm going to change it a little bit. I'm going to say move immediate ACC, and then I'm going to say the out 81, the MBI A, comma 87, like we did before, out 81. Now I'm going to type return, and I'm going to say L100 to make sure I know what the heck I've got here, make sure it's exactly what I want. Load A with CC, out 81, load A with 87, out 81, and then return. Now what I'm going to do is I'm going to quit DDT, and then I'm going to save this memory image as a executable file. So we can run this as a program on a command line instead of having to type it in every time. So the way you get out of DDT is you type G0, and you say save 1. Now that's 1 256 byte page from address 100 in the memory into some file like green.com. All right. Now if I type green, it'll load that program, run it, and it should hopefully come back to the prompt, which is exactly what it did. Now it changed it to green, changed the foreground color and the background color to green, and nothing's on fire. I have no idea what mode the chip is in or anything. I haven't read the details on that. Now, the fact that I changed the foreground and background to green, if it's filled with random pixels and they're all the same color as the background, it would still all be green. So this is not a good choice. So let's say I want to edit an existing program. I can also do this, and I can type L, and we can see it's sitting in there again, right? So I can change this to A100. I can say move immediate A with some other pair. I don't remember. Anything would probably work if I type CA instead of the CC. What I've done, if memory serves, is I've just chosen two different colors. One for the foreground, one for the background. They're just different colors rather than making them both green. Should probably call it rando.com. And this will set something else. So now I've got yellow. And that's looking pretty good. Of course, we're driving it directly off the 99 or the 9118. Maybe what we should do at this point is look again at the video output driver. And for that, I'm going to use the green, and I want to create a white program. So white is F, okay? So let's look at this program here. I'm back in DDT. Let's say MVI A, comma, FF. Oops. Keep making the same mistake. MVI A, comma, FF. So I'm going to say white and do all that. Go to 0. I'm going to say save. One is white.com. And since this name makes no sense anymore, let's do this right. VIA, comma, CC, which was the green one, right? Okay, so go to 0. Save one as green.com. Now when I run the green program, it should be green. When I run the right one, white one, it should turn white. Okay, perfect. Now let's come back and look at this again here for a minute. As I said before, this doesn't make a lot of sense to me. And I saw some noise and I was playing around on the breadboard. This makes sense because that's what the manual says to put in there. Just about everyone's got a driver like this, whether it's a 3904 or a 2222 or a 4401. Any general purpose NPN transistor should do here, okay? I don't see this happening. All right, this R2 thing. So I am basically going to say forget it. I'm going to put some X's on here so we'll kind of remember here. X, I'm going to say DNP R2. All right, make this font big, whatever. Is that huge? Oh, yeah, that's big. Oh, it already says do not populate R2. That's great. Let me just edit this statement then. R2, and I'm also going to leave out R4 because I think that's worthless as well. Mostly because, oops, come on. It's going to go through 33 ohms and then, look, video inputs on consumer devices, and that's the key here, have a 75 ohm terminator on its input. So this 330 is actually in parallel with the 75 over here. So this one doesn't really, it seems to be of no real value, in my opinion. I'm going to change this thing to a ferrite bead. And I'm going to build this up on a breadboard. I could do this, obviously, on the PC board, but I'm going to do it on a breadboard so that we can play around with it and change the sizes without having to resolder the parts and all that. All right, so here is the Retro, the way we left it last time. It's running. We got the DRAM. I take the video output signal here, and I run the wire over here on this breadboard. This is exactly the circuit as I've just described it in the schematic we were just looking at. And we have what? There's the ferrite bead. We got 5 in ground. I tap that off this SD header over there to get my power. I've got a 10 microfarad. There's the 0.1 filtering the power. That's the 470 terminator coming off of the video from the VDP. There's my 4401. The collector runs up to 5 volts. The emitter goes to 33 ohms and out to the video capture card. All right, so the first trace we have here is we're running the white signal. And you can see the bottom cursor is on black. The top cursor is at, well, actually, that's running a little hot, which you can see with the delta Y off to the right there. It says 740 millivolts. It should be exactly 700. And I think I'm good. I probably should have done a better job aligning those cursors. Sorry about that. Now we've got the green signal with the same cursors. That's looking pretty good. The next one is white again, and now I've moved the bottom cursor down to the sync tip, and from the bottom sync tip to the top of the white is supposed to be 1 volt, and that's looking pretty good. Next, we zoom in a little bit on the white signal here. You can see the 5 o'clock shadow on this thing a little bit. You can see the color burst in there just after that super low sync signal. It looks good except for that little fuzz on there. This one here is what happens if I unplug the video capture device. So now it's unterminated completely, and you can see the thing is all out of whack. It's got some droop in there. Not surprising. This is what it should look like in this situation. Now let's reattach the video capture device so we got the right termination and zoom way in on the color burst signal there. As you can see, this has got a lot of super high frequency fuzz on this thing. Now, I found a design where they had like a 380 puff capacitor that filtered the output to ground, similar to what I'm doing here. If I can get it to go into my perf board. Now this should get rid of the super high frequency noise that's coming out of the video here. We look back at the scope now and we see it's quite a lot better. Here's what it looks like after, here's before, and here's after again. Now, I'm pretty sure this won't change the way the picture looks on the screen, but what it really does is it gets rid of high frequency nasty noise that's going to come out that cable, and that is going to get rid of your unintended RF emissions noise and stuff like that. So I'm sure what I was looking at was a schematic used in a commercial product where they had to get like an FCC rating or something like that. And you definitely don't want to have all this high frequency chatter all over the place coming out of your product. So I'm going to go ahead in the next rev and pin out a place for this capacitor to go, so we can all try to get rid of our unwanted RF radiation. All right, so and that brings us back to our friendly neighborhood DRAMs here, which I successfully put out of my mind for 15-20 minutes there. Okay, so we have a chip plugged into U2 right now. We do not have one in U1. So that means that the VDP down here, whenever it writes any data, half the byte is thrown away. Whenever it reads the data, half the byte is not being driven by anything. It get noise or something. I don't know what it will. Probably, usually it will float high. If this is probably a MOS chip, so it's unknown. I think those bits will be floating and doing crazy things. It's probably not nice to do that to MOS I/O pins. But at this point, you know, hey, calling me crazy. So I'm going to leave this one in here. And I'm going to try and see if we can recognize something is functioning here. And to do that, we're going to need to go back to the manual. We actually have to read this darn thing. You know, how long can we put off the inevitable, right? Learn how to actually program this thing. So if we scroll down a little bit, we already know about the registers and all that. Take a quick recap here. The VRAM, you can write into the VRAM, you can read back from the VRAM. So we should be able to interact with the video RAM directly from the Z80 if we want to. Now we know that we can write to the VDP registers because we've been doing that all along. That's how we set the background color and all that other fun stuff. I've yet to read the status register to try to make sense of it. In fact, we haven't read from anything on the VDP yet. For all we know, that doesn't work. We should verify that. And we should try to figure out how to interact with the RAM. So what do you got, this mode thing? A normal human would call that an address bit, right? So we connected that up to A0 in the schematic. The read and write signals are these, okay? It's port address 0 and port... This is in their evaluation board design or whatever, arbitrary chosen for this guide, all right? So for us, that's ports 80 and 81. These down here is what we've been using for port 81. These up here would be port 80 in hex. So we can write to the VRAM and we can read back from the VRAM. So now it's a matter of figuring out what that means, okay? For the VDP registers, we've already read and played around with that. Here's how you read the status register. You just simply read it. Okay. VRAM. Okay, so what you have here is this idea that you continuously write bytes out into the VRAM write port address. And inside the VDP, there's an automatically incrementing counter. So what you're really doing is you just outputting bytes one at a time, and the VDP puts them in continuously subsequent higher numbered RAM addresses, okay? Which is convenient. So once the address is once the address to read or write has been set up, and the first 2 bytes that you transfer with the VDP, we can read or write a byte of data using 1 byte transfers. Continuing will cause the address to increment in the obvious way. Therefore, reading or writing a sequential chunk of data can be performed very quickly. Depends on your definition of quick. But in those days, yes, absolutely, it would go faster. What do we got? The mode signal is high for the first 2 data transfers, which is the address setup, and then low when you're actually reading or writing data to the VRAM. So what that means is we want to set up the address, which is 13 bits of data. What we're going to do is we're going to write 2 bytes out. And then we're going to be able to write as many bytes as we want into the VRAM, starting at the address that we send over up here, okay? Now remember, TI likes to do everything backwards. apparently even the power pins. Now, in their defense, of course, I don't know who invented that particular pinout in that chip. I don't know who did, but it just, yeah. Moving on. In this context, look, this over here is what we would call address bit 0, 1, 2, 3. Everyone on Earth, other than perhaps the only time I've been exposed to this backwards numbering has been with the IBM mainframe and TI chips in general. It's possible that Motorola did this. I don't know. The 68K is big endian, but this is bitwise big endian, which is unusual, at least in my narrow experience of life, okay? So keep in mind a 0 through A7 from the perspective of the Z80, all right? And then this is going to be a 8 through a 13 here. And then it says, what do we got to do? When we write, what are we doing? We write a byte out in mode 1, so that's port 81. Then we write a second byte out to port 81 that has a 0, 1 up here, followed by the most significant 6 bits of the address. And then we can write out bytes continuously, one at a time, to port 80. And it'll pad, or write all those bytes into the video RAM one after another. Now, what I'm thinking here, well, let's look at the read really quick before we move on to the next thought. Just like writing, you get the address that goes out, and then you've got a data transfer that takes place. So for whatever reason, when you set up to start writing data into the video RAM, you have the first byte and the second byte that has a 0 and a 1, the most significant 2 bits. When you want to do a read operation, you do the exact same thing, except when you put out the most significant 6 bits of the address you want to read from, you have to have a 0, 0 in the most significant 2 bits. Then you can continuously read bytes one at a time from the video RAM, starting at this address, and you then will be able to read them one after another from the VRAM. Let me give you a scenario. Suppose you want to write 0 into that there. You can do this, that, and the other thing. And suppose you want to read from memory here. The first byte transferred to what we would call port 81 would be the lower address byte, which is the A0, and then the second one goes be the 20. X is now set up to be that. You can do the reading and blah, 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 blah. And then they go on to whatever's going on. Okay, so let's write a little program that sends a bunch of data into the video RAM and then tries to read it back out. That'll let us know if the thing is working or not. Okay? Keep in mind, we only have only got 4 bits of memory in there. But otherwise, my gut is that this should work fine. Just half of it, right? We've got, what do we got in there? We got U2 in there, so this is what I would consider the most significant byte. But remember, this is all probably backwards. So the RD7 and so on is probably the least significant hex digit. Okay? Alrighty, so let's, what are we going to do here? We need to, let's just go DDT. I'll spare you my typographical errors. So I created a DRAM.com file here, and this is what's inside of it, all right? So I'm going to set this up so I can write into RAM address 0, or video RAM address 0. So I'm going to put a 0 in the accumulator. I'm going to output that in port 81, and then I'm going to do the 40 here, right? Now remember, there's a 40 because when I'm setting up my write address, the first byte is the least significant half of the address. I'm writing to address 0 anyway, so it doesn't matter what I send. They'll all be zeros. But I got to have this bit set on in the second of the 2 setup bytes that I write over to port 81 here. So that's why there's a 40 there, right? So 00 and 40, that's the second and most significant bit set there, and that's what goes out there. And then I'm going to put a 0 in the memory at that address. Then I'm going to put a 1-1 in there, then a 2-2, and a 3-3. I'm going to just put something so I can recognize what's going on. Now, I'm putting it in both halves because, you know, with all this high, low, backwards bit ordering, I have no idea where this is going to go. So let's just do this so maybe we get something that we recognize coming back. So then what do? We want to read it back. So at this point, we write out our least significant byte of the address we want to read from and put that in port 81. And then we write the most significant 6 bits of the address that we want to write, or read back from, I should say. And we write that out on port 81, right? So where's the manual here, right? So reading. And when we write that second byte out here, we got zeros up here. So in this case, it'll just be 00 and 00 for both of these. Yes. And then after that, allegedly, we can just read a bunch of times and get data. Now, this is, I wrote a nice little loop here, so we should be able to trace this. And what we get back over here, we should recognize as having been constructed, having been based on these bytes that we wrote in the first place. Now, we're reading out more than we wrote in, so we'll get some garbage at the end, right? So we should be able to see a 0, 1, 2, 3. I suspect in the least significant digit as we read back down here, and we'll get garbage, presumably, in the most significant hex digit when we're reading. So let's make sure we're at the right place. Yes, we are. So if we do a bunch of traces, there's the 1-1, and there's the 2-2, there's the 3-3, okay. Now we're going to set up our address for reading, and these go to port 81 and port 81 for the second byte, and then we say input 80. Now this is a pre-trace register dump, so we should have just read in the value into the accumulator. Oh, pre-trace register dump. So the next thing we do, if I hit like R, I should see the what? I don't know what I just did. Oops. I think it's X to see the value of all the registers right now. Yes, okay. Program counter is at 122. That makes sense because it's a 2-byte instruction, and we got 0 in there. Now, we did write a 0 in the first byte, and that one should be 0. Okay, so we can read it again. And we say X, we should get, goody. Oh, we got a 1. So maybe I didn't blow up that DRAM is what that means. Now, if I do another trace and dump the registers, unbelievable. How did I not blow up that chip? Hooking the power up backward. Yeah, that's the luck. I blew it. I could have played the lottery today, and I could have gotten something out of it. Okay, so we run a 00, 01, 22, 3 in there, and we got 1, 2, and a 3 back. And now we're getting the garbage bytes in here. So if I just simply keep tracing and we watch what happens, A has a 0 and an F and a 0 and an F. So that's not too shocking because we didn't save anything into those addresses. This is very promising. Almost makes me want to hook up that other DRAM. But you know what I really want to do is see if I can get some video to come out that has just bits and pixels in it. So what we need to do is probably set the registers in the VDP to go into, it's got a couple of different modes, how many columns and rows of characters, and is it text mode, is it graphics mode, and all this other stuff. And I have no idea what mode it's in. When the thing boots up. So you get the graphics mode, multicolor mode, text mode. I don't know. I don't even know if I can read back the current mode. These are write-only registers, which is wonderful, right? So it's not clear how this thing really works. Down here, it's not clear how to find out what mode you're in, is my point. So when you're writing all this, what you're really doing is you're configuring things like where do all the bit patterns for the text characters where are they located in the video RAM? Okay, so this is why they're saying, write this into register 2, and here's where the address comes from, that it dictates where the data comes from that it's going to paint on the screen. And this is the color table for something, and what else do we got in? Here's our favorite register 7, which is the foreground and background color of the text. And then we got a status register. What do we get back out of here? It needs the interrupt flag, coincidence flag, fifth sprite, and the fifth sprite number if one exists. These are explained in the following paragraphs. This is, every time you get one video frame drawn on the display, the VDP can generate an interrupt back to your CPU so that you can synchronize yourself to the screen. Now, the Retro has a minor problem with this. First of all, I didn't even hook it up, right? Because that's a diode in the header that I didn't even solder into the board, but that's beside the point. If we route this interrupt back to the Retro, this will only work if we're in like mode 0 or mode 1. And if you're using interrupts from the SIO or the CTC, that'll only work if you're in mode 2. So this is not a great thing right now, but we can play around with it. It's just a little bit limited in what we can do when we're generating interrupts from the VDP. That's all. Fifth sprite has to do with you can only have so many sprites per line. And if you have more than 4, you have a problem. And it'll tell you this is the fifth one that it would normally want to be drawing on the screen, but it's too complicated for the simple circuitry in there to do. So this helps you figure out what's going on the screen. If sprites are, if there's a lot of sprites in one horizontal scan line on the screen. If 2 sprites are over top of each other or colliding, this bit here will be set. So if you wrote a video game and you're moving sprites around on the screen, you don't even have to calculate whether or not they've run into each other. If one of them's a photon torpedo and the other one's a spaceship, this thing will let you know if 2 of the sprites have collided, and then you can figure out what to do about that in your code. So it's a useful little feature here. Now, trying to figure out if 2 rectangles overlap is not too hard to do, but I suspect this might also work if a sprite is not exactly a rectangle, which is more of a complicated thing to figure out. We'll talk more about that when we play around creating sprites and try to make a Pong game or a breakout game or something with this thing and play around with that later. Point of bringing all this stuff up right now, as far as I can tell, I cannot read any information about what this thing is doing. Therefore, it is completely my responsibility to write all these registers and set them all up into some mode in order for me to know what mode the thing is in, because there's no way to ask it. What does it say here? Registers 0 and 1 contain the bits to enable various features and modes. 2 through 6 contain values that specify the addresses of the VRAM locations that we were just looking at. Some of that a minute ago. Okay, so tables are used to generate all the patterns and all that other fun stuff. 7 contains the color of the text when you're in text mode, and it contains the backdrop color for all modes. Some registers are not. All bits are used. Put zeros when you're not for the undefined ones. Okay. And repeatedly note our numbers are backwards. Okay, so we what do we got here? The register 0, external video, and M3. So we've got these different modes we can put the thing in. One of the 3 bits. The other 2 bits that specify the mode are in register 1. So M3 here is right there. Activate 0 to disable the VDP plane. That I mentioned before, there's an input bit on the chip that says, if I want to, I can draw graphics on top of a video signal that can pass through the chip, so you can do a text overlay. I didn't hook that up, so we don't want to do that. So I'm going to put a 0 in here. In theory, we could just write a 0 into the whole register. That would mean we could be in graphics mode or text mode or multicolor mode, whatever those modes are. Let's just put it in graphics 1 mode, no problem. I don't even know what that is, but it'll probably do something, right? Register 1 has these bits. All right. What do we got? Bit 0. This is the most significant bit, remember. How much RAM you've got. Only used... okay, so we don't care because we have 16K anyway, and this only works with 16K, so we're good. Blank. I wonder if this is set to 0 because we never initialize it. It enables the display. That's probably why we don't have anything on our screen. Blanking causes sprite pattern to blank out, whatever that means. But it still allows a backdrop to show through. Blanking does not destroy any tables. So I'll bet we're blank in the backdrop, what I would call a background color, is what we're seeing on the screen. Awesome. So no, we don't want to enable any reps. They're not going to do anything anyway. These are the other 2 bits for the mode. Reserve, sprite size. You can have big sprites, little ones, and stuff like that. And then you can even have like double size, even if they're big or whatever. And then we got all these other address registers it mentions above. You know what? Let's just set this to mode 0. What do we got here? What if I just put 0 in all these bits? That's a don't care. Blank screen. Oh, no, we need that to be a 1. Okay. No interrupts. Make that 0, 0. And we don't care about the sprites yet. So this has to be a 40 in hex. And this one up here can be a 0. And that's register 0 and 1. Let's go and what are we going to do? We're going to do ddtgreen.com to get some basic thing. L100 if I do it right. Okay, so we set the foreground and background colors to green. And then we return. This is the green program. Okay, so let's just write a new program. You know, it's so hard when there's only 8 instructions. Move immediate A with let's pick some other colors here. We remember that we need to write a 40 into this and a 00 into the register 0. So that's 00 and then 40 for 0 and 1. What I need to do is look up some colors. So let's get some contrast on there. So let's go with we could go with black. We can hedge in our favor so it doesn't look too ugly. If we choose black and actually it doesn't matter. We're not going to use the text foreground, but let's use different colors though, so that if there is something and it matters, foreground, background, we'll get something. So black is 1 and green is fine with me. So that's C1. All right. Actually 1C, because I believe the background is the second digit in there. And we're going to say out 81. And then if we list 100. So we got 2 different colors this time. And then we write that in register 7. And now down here at A108, we're not going to return. Instead, we're going to move on our merry way. And we're going to write some stuff into registers 0 and 1 here. Okay, so I'm going to put a 0 in this one. Okay, so I'm going to say move A with 0, out 81. Move immediate A with 40 in hex, out 81. Now, we can get rid of this here, so it's 40. Don't blank the screen. And it would actually make sense that maybe this is set when the thing powers on. So I'm going to enable the display, and I'm going to be in mode 0, whatever that means. and there's stuff in the chips, so hopefully there'll be visual noise on this screen. I am return. Okay, return list 100. So we got a foreground, background colors that are different. So register 7. I'm going to put a 0. Oops. I'm just writing values. That's not what we want to do. I want to say put a 0. Then I want to say a simple 10. See, oopsie. So I want to do this. And I want to output that on port 81. And then down here, I have to write the register number with the most significant bit. So that's actually, I got to say move immediate A, comma 80 in order to write that into register 0. Then I want to say move immediate A with 40. And then I want to say out 81. And then I want to say move immediate A with 81 in order to write that into register number 1. And then I'm going to say out 81. And then I'm going to say return. And let's see if that makes sense now. 1C goes to 81 for register 7, out 81. So that's me writing 1C into register 7. Now I'm writing 0, oops, into, I forgot, oh my gosh, okay. Maybe I should have written a real, I should have used an actual assembler for this. I'm a little out of practice here. So I'm going to out 81. Let's look at it again. Okay. So I got 1C to register 7. Now I got 0 to register 0. Okay. Now at this address here, I need to say move immediate A with 40 in hex, out 81, and then move immediate A with 81 in hex in order to write it out to register 81, out 80, it's rather write it out to register 1, for crying out loud. I've been doing this too long today, I think. Let's see what's going on here. 1C to register 7, 0 to register 0, 40 to register 1, and then return from subroutine. So this should put it in a graphics mode and not blank the screen and return back to CPM. So if I save this, save one page as whatever, mode1.com. Let's run this thing and see what happens. Where's my screen here? It's still set to white. Please do something. That, combined with the other SRAM stuff, strongly suggests that the DRAM chip's working. You know, I'm going to hack that other one in there. And then next time when we get together, maybe we can actually try to write an actual graphic program and see if this thing, maybe get sprites and stuff on there. I didn't, well, at least one of the RAMs that's in there right now didn't burn up. Maybe the other one didn't either, and we can actually do something. You know, this doesn't look half bad. It really doesn't. That's kind of crisp, and let's zoom way in here. All right, now it's looking bad. You can actually see a little bit of artifacts in there, which is not going to be shocking at all. I mean, these things in this era, this is the kind of thing. This is what happens with composite video, period. All right, and this also is probably, this is like a $10 capture device, so it may not be the highest quality, and it could be having trouble dealing with the color phase and the color burst signal. If you Google around a little bit, and you can find out all kinds of crazy stuff about NTSC video and why you end up with all these weird artifacts and what they call dot crawl and stuff like that, due to the way that, you know, there's all that information encoded in one single waveform, you know, the luminosity as well as the color information. That's what happens, you know. Anyway, for this, this is awesome considering how bad. The mistakes have been with this. This is fabulous. I love it. We'll see you next time. Maybe we'll actually get both chips going and do some real recognizable diagrams on here. Thanks for watching. See you next time.